we now know what a probability distribution is. It could be a discrete probability distribution or a continuous one, and we learned that that's a probability density function. Now let's study a couple of the more common ones. So let's say I have a coin, and it's a fair coin, and I'm going to flip it 5 times. Flip 5 times. And I'm going to define my random variable x. I'll make it a capital X. It equals the number of heads. Number of heads I get after 5 flips. After 5 flips. Maybe I flip them all at once. Maybe I have 5 coins and I flip them all at once and I just count the heads. Or I could have 1 coin and I could flip it 5 times and see the number of heads. It actually doesn't matter. But let's say I have 1 coin and I flip it 5 times, just so we have no ambiguity. So this is my definition of my random variable. As we know, a random variable, it's a little different than a regular variable. It's more of a function. It assigns a number with an experiment. And this one's pretty easy. We just count the number of heads we got after 5 flips, and that's our random variable x. Let's think about a little bit of what are the different probabilities of getting different numbers here. So what is the probability? What is the probability that x, big capital X, is equal to 0? So what's the probability that you get no heads after 5 flips? Well, that's essentially the same thing as the probability of getting all tails, right? This is a bit of a review of probability. You'd have to get all tails. And what's the probability of each of these tails? What's 1/2? So you'd have to be 1/2 times 1/2 times 1/2 times 1/2 times 1/2. So it'd have to be 1/2 to the 5th power. 1/2 to the 5th power, which is 1 to the 5th is 1, over 2 to the 5th is 32. Fair enough. Now what's the probability? And this will be, I'm going through all of the, a little bit of a probability review, just 'cause I think it's important just to get the intuition of where we're going now and how you actually form a discrete probability distribution. Now what's the probability? What's the probability that you get exactly 1 head? Well, that could just be the first head, right? It could be heads, then tails, 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 tails. Or it could be the second head. It could be probability of tails, heads, tails, 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 and then so forth. This 1 head that you get, it could be in any of the 5 spots, right? So what's the probability of each of these situations? Well, the probability that you get a head is 1/2. Then the probability of your tails is 1/2. Times 1/2 times 1/2 times 1/2. So the probability of each of these situations is 1 over 32, just like the probability of this particular situation. In fact, the probability of any particular order of heads and tails is going to be 1 out of 32. There's actually 32 possible scenarios, right? So the probability of this is 1 out of 32. The probability of this is 1 out of 32. And there's 5 situations like this, because the heads could be in any of the 5 spots. So the probability that we have exactly 1 head is equal to 5 times 1 over 32, which is equal to 5 over 32. Fair enough. Now it gets interesting. What is the probability? I'll do each of these in a different color. What is the probability that my random variable is equal to 2? So I flip the coin 5 times. What is the probability that I get exactly 2 heads? Now it becomes a little bit interesting. So what are all the situations? I could have heads, heads, tails, tails, tails. I could have a head, tails, heads, tails, tails. And if you think about it, there's these 2 heads, and they can go in a bunch of different places, and it starts to get a little bit confusing. You can't just think of it in kind of this scenario analysis like we did here. You can, but it becomes a little bit confusing. Well, you have to realize one thing. Each of the scenarios, there's a 1 out of 32 probability, right? 1/2 times 1/2 times 1/2 times 1/2 times 1/2. So that's a 1 out of 32 probability, right? Each of those. Now we have to think about how many of these scenarios satisfy our condition. 2 heads. So essentially we have, you can imagine, we have 5 flips, and we're going to choose 2 of them to be heads. Right? So you can almost imagine like if you had all of the flips sitting around and we had 2 chairs and we said, okay, whichever flips sit in these chairs, they get to be the heads chair, right? Or they get to be the heads flips. And we don't care in order of what order they sit in. And I'm going someplace with this just so you get hopefully a little intuition. And you might want to watch some of the probability videos on this when I talk about the binomial theorem and all of that, because I go into this in a little bit more detail. But if you think about it that way, the binomial coefficient kind of starts to make sense. Because if you think about, okay, I have 5 heads. I have 5 flips. Sorry, who's going to sit at which flip is going to be the first heads? Well, there's 5 possibilities, right? Let me do this in a different color. There's 5 possibilities for which of the positions or which of the flips is going to be the first head. Now, how many possibilities are there for the second head? Well, the first flip that we used up one of the heads chairs, right? Or sorry, the first heads chair, the first head spot was used up by one of the flips. Now there's only 4 flips left. So there's only 1 out of 4 flips that the second head could be in. And you saw that here. I picked the first one to be a heads here, and then we said, okay, one of these 4 also have to be a head. Or if I said, okay, this is the first head, then either this one, this one, this one, or this one has to be heads. So there's only 4 possibilities. So all I'm saying is, the first time around, there's 5. You have 5 different possibilities for where the first heads could be, and then the second time around, you have 4 different possibilities. And you have to think about it. When we count it just like this, we're being dependent on order, right? But we don't care which flip is in which heads. We're not saying that there's kind of a, we're not saying that this is a heads 1 or this is a heads 2. These are both heads. It doesn't matter. We could have this being the flip, the head seat 1. This could be head seat 2, or it could be the other way around. This could be the second head spot, and this could be the first head spot. And I'm saying that just because it's important to realize the difference between a permutation and a combination. We don't care about order. So there's actually 2 different ways that this can happen. So we divide it by 2. And as you'll see, it's actually 2 factorial ways that it can happen. If this had 3, we would do 3 factorial, and I'll show you how that can happen. And so this will be equal to 5 times 4 is 20 divided by 2, which is equal to 10. So there's 10 different combinations out of the 32 where you have exactly 2 heads. So 10 times 1 out of 32 equal to 10 over 32, which is equal to what? 5 over 16. 5 over 16. Now what is the problem? And actually, let me write this in terms of a binomial coefficient. This up here, that number right there, if you think about it, that's the same thing as 5 factorial over, what's 5 times 4? 5 factorial is 5 times 4 times 3 times 2 times 1. So if I just want 5 times 4, what I can do is I divide 5 factorial divided by 3 factorial. Right? This is equal to 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. And you're just left with the 5 times 4. So this is the same thing as that. And then, since we didn't care about order, we wanted the 2 here. And it actually turns out that it's 2 factorial. And I'll show you that in a little bit. It's 2 factorial times 1 over 32. This was the probability that our random variable, that we have exactly 2 heads. Now what's the probability that we have exactly 3 heads? The probability that x is equal to 3. So by the same logic, the first head spot can be taken by one of the 5 flips. Then the second head spot could be taken by one of the 4 remaining flips. And then the third head spot could be taken by one of the 3 remaining flips. And then how many different ways can I arrange 3 flips? In general, how many ways can you arrange 3 things? And it's 3 factorial. And you could work that out, or you might want to watch the probability videos where I work that a little bit better. But actually, if you just take the letters A, B, and C, there's 6 ways that you can arrange these, right? You could view these as the head spots, and we don't care about order. So it could be, A, C, B, C, A, B. It could be B, A, C, B, C, A. And then what's the last one that I haven't done? It's C, B, A. Right? There's 6 ways to arrange 3 distinct things. We're dividing by it because we don't want to double count these 6 different ways, because we're viewing them all as the same thing. Not in this case, but in the case of we don't care which flip is sitting in which head spot. So that's why I got the 3 factorial. And this is the same thing. 5 times 4 times 3, this could be written as 5 factorial divided by 3 factorial, and then this is divided by 3 factorial. This one is this one. And so this is equal to, I don't know what that's. See, 3 factorial is equal to 3 times 2 times 1. The 3's cancel out. This becomes a 2. This becomes a 1. Once again, 5 times 2, so it's 10. And then it's 10 and times, and there's each situation has a 1 in 32 probability. So once again, it's equal to 5/16. And that's interesting. The probability that you get 3 heads is the same as the probability you get 2 heads. And the reason that, well, there's a lot of reasons why that's the case, but if you think about it, the probability of getting 3 heads is the same thing as the probability of getting 2 tails, right? And the probability of getting 2 tails should be the same thing as the probability of getting 2 heads. And so it's nice that the numbers work out that way. It's nice that the numbers work out that way. All right, so we're almost there. What's the probability that x is equal to 4? Well, we could use the same kind of formula now that we've been using before. You know, it could be 5 times 4 times 3 times 2. But so it's 5 times 4 times 3 times 2. All the way, you know, how many ways can you arrange 4 things? It's 4 factorial. 4 factorial is essentially this thing right here, right? 4 times 3 times 2 times 1. You know, this is 4 times 3 times 2 times 1. So these cancel out, so it's 5. And then each of the scenarios has a 1 in 32 chance, so it's equal to 5/32. And once again, notice the probability of getting 4 heads is the same thing as the probability of getting exactly 1 head. And that makes sense, because 4 heads is the same thing as getting exactly 1 tail, right? And you say, oh, where's that 1 tail going to be showing up? Oh, there's 5 different spots for it. And each of the scenarios has a 1 in 32 possibilities. And then finally, what's the probability that x is equal to 5? You get all 5 heads. Well, that's going to be, you know, it's going to be heads, 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 heads. Each of these have a 1/2 probability. You multiply them, you get 1 out of 32. Or another way to think about it, if you think about the 32 different ways that you can have heads and tails in these experiments, this is only one of those circumstances, right? This was 5 of the circumstances. This was 10 of the circumstances. Anyway, we've done the work now. We're ready to draw a probability distribution. And I'm running out of time. Actually, let me continue that in the next video. And maybe if you're in the mood, maybe you draw it before you watch the next video. See you soon.